we're going to do a very simple test of validity of some XML. It's not a full test at all. We're just checking whether the angle brackets are matched. Here's some test data that we can work on. The first one is valid, and the second one is not valid. And that's because when it says 2 is less than 3, it uses an angle bracket there, which messes up the balancing of the angle brackets. There are 3 rules really that we need to keep here. One is that every opening angle bracket has a closing angle bracket. That is, every less than sign has a corresponding greater than sign. Another rule is that they cannot be nested. And well, finally, meaning we can't have less than, and then greater than. And then, well, you could say it's not really an extra rule. We have to finish up with everything closed. It can't be shifted around. Okay, let's get started. We're going to define this entirely tacitly from the beginning. So let's apply this function to each one of the test cases. And what we're going to do is note that the only thing that matters for our problem are these angle brackets. We don't care about any of the other characters. So we can start by filtering, so we only have these angle brackets and none of the other characters. And one way we can do that is by doing an intersection. So we're treating the arguments as sets. And we're going intersection between that and the angle bracket. So now we can see we've isolated out only the angle brackets. That makes it much easier to work. The strategy we're going for here then is to identify where we have such pairs, because the entire argument now must be made out of entire pairs of open, close, open, close, open, close. When we get here, we get open, open, and that's wrong. So one way we can do this is by searching for angle brackets. So we're now going to change the intersection function into a compound function, a fork, where we're going to find, so this finds locations of what? Of the right argument. So this function here has a very interesting structure. It is bound with a right argument, which are these angle brackets, which means that when we apply it to some text, that text becomes the left argument. And then it's called a fork because it kind of branches out and applies the two outer functions to the arguments, and then the middle function to the results of those two outer functions. So this is the intersection of the left argument, which is going to be the text, and the angle brackets, which have been bound on the right. This is the right side identity function. It ignores the left argument and returns the right argument. So we again get the angle brackets. And this returns a Boolean mask, same length as the argument, with a 1 every time what we're looking for starts, including overlapping matches, but that's irrelevant in our case. So here we have the Boolean mask, and we can see that we have open, close, open, close, open, close, and so on. Down here, we have open, close, and then we have one character that doesn't belong there, and then we continue with open, close. What we can do now is check that the entire mask that we got out consists of uninterrupted 1 0 1 0 1 0 and so on unto the end, and it has to also end with 1 0. If the final character is not, or the final characters are not open close, then we wouldn't get a 1 0 at the end. If the final character is an open, we won't get a 1 at the end because we're not finding the entire open close. And then the find function will not say we get a partial match. So we don't need to check for any of those extra rules, we could say, whether the they actually match or not, whether we're closing at the end. We have all boiled it down to this subset of the input consisting of open closes, which are then mapped to ones, zeros. So we can apply another tacit function to that, where we take the argument length and use it to reshape 1, 0 as a constant. So this operator takes the 1, 0 and makes it into a constant function. It's again the same structure with a fork as we had before, but this time only with one argument. So we apply this constant function to this mask that we got out. That gives us 1, 0. We apply the tally function, so it looks like a tally mark, which gives us the length of the mask that we got out. And then we use reshape, so it's a Greek rho, R for reshape, to reshape the result of the constant function, which is 1, 0, into the full shape, cyclically. So 1, 0, 1, 0, 1, 0, until we get the full length. And then the only thing we need to do is to check whether this mask matches this mask. That is, whether this mask matches this mask as well. And we are given the mask as argument here. We used it to get the tally, the length, and we have this right identity function that we can apply. So this also corresponds to the mask. We're asking whether it matches exactly, element for element, the mask that we've generated here. We can see the first one is good and the second one is not. And that's actually our whole solution. We can assign it like this and apply it to each one of the elements of T. Thank you for watching.